Hello, welcome to the lecture on sketching Bode plot, part 1. We have already discussed in the lectures part 1 and part 2 regarding the basics of Bode plot and what are the basic factors in a transfer function. Before starting this lecture, I want to introduce you to I want to refresh again what we have discussed in the previous classes. Like in any transfer function, you will be definitely having these basic factors, right? We know one is a constant, another is an pole at 0 and 0 at the pole at 0, 0 at the origin, then pole at minus a, 0 at minus a. And we know when k is greater than 1, the constant, for a constant, the 20 log magnitude will be a positive. When the k is between 0 and 1, the magnitude 20 log k will be a negative and it will be as a constant. The phase angle of any constant is 0 degree. And we also discussed that for a factor of 1 by s, the slope would be minus 20 dB per decade. This can be extended to 1 by s power n. Like 1 by s square means minus 20 into 2. 1 by s cube means minus 20 into 3 decibel per decade. Okay, for 1 by s, the phase angle is minus 90 degree. For 1 by s power n, the phase angle is minus 90 degree into n. Similarly, for s, let's say 0 at the origin, the slope is plus 20 dB per decade and the phase angle is plus 90 degree. And if I extend this to s power n, it becomes plus 20 into n and the angle is 90 degree into n. Then for the factor 1 by s plus a, it will be having a corner frequency. What is the corner frequency is a. Okay, here we have two conditions. When the omega is less than a, that is omega is less than omega c and omega is greater than omega c. Right? It is omega greater than corner frequency, omega less than corner frequency. For less than corner frequency, it is 0 dB. For greater than corner frequency, I can approximate and write it as 20 log 1 by omega. Okay. And the phase angle it's minus tan inverse of omega by a. We know tan inverse ranges from 0 degree to 90 degree. Since we have minus sign, it's minus 0 degree to minus 90 degree. Likewise, for the pole at the for 0 at minus a, we have a corner frequency omega equal to a. In this case, for omega less than omega c, we have 0 dB. For omega greater than omega c, we can approximate it as 20 log omega, that is plus 20 dB per decade. And what is the phase angle is tan inverse of omega by a. We know for tan inverse, the angle ranges from 0 to 90 degree. Right? Now, we have to see where we have used those Bode approximation. Right? If you look at the three terms for the constant k, 1 by s, yes, these are all going to work at all omega. They are the exact response. They are exact. All these three are exact. We never do any approximation, right? And if you take the cases 1 by s plus a and s plus a, here we have a corner frequency. For both the cases we have corner frequency, we approximate, right? These two are approximate. Okay, these things we discussed in the previous lecture itself. Just a quick recapitulation. We are discussing these things again, right? Now, we move into a problem. We take a transfer function g of s given as 3s by s plus 4 into s plus 2. First thing we have to start with the corner frequency. What are the corner frequency? If you look at the s term, we don't have any corner frequency. What is the corner frequency of s plus 4? In the first slide we have seen s plus a. In the corner frequency is a. Here s plus 4. So the corner frequency is 4. S plus 2. The corner frequency is 2. We have to name it like omega c1, omega c2, corner frequency 1, corner frequency 2 in the ascending order, right? So 2 is the first corner frequency, 4 is the second corner frequency. The second step would be like writing the given transfer function g of s in Bode form. We discuss what is Bode form. Bode form is nothing but writing in 1 plus s format, right? Here you can see it is in 4 plus s, 2 plus s. So I have to convert into 1 plus s format, 1 plus s format. So what should I do? I have to take 4 outside, I have to take 2 outside from the denominator. Okay, so that's what I'm doing here. I'm taking 4 outside, so this becomes s by 4 plus 1. Taking 2 outside becomes s by 2 plus 1. So 3 divided by 4 into 2, 8. So 3 divided by 8, s divided by 1 plus s by 4 into 1 plus s by 2. This is the Bode form. Okay. Now we have to find the frequency response. We will substitute in place of s with j omega. Once I substitute, the expression, the transfer function becomes like this, right? Now we know any complex number or any to find the response, frequency response, we have to go for the magnitude and phase angle, right? What is the magnitude? Okay, 3 by 8, magnitude of j omega is omega, magnitude of 1 plus j omega by 4 is 1 square plus real part square plus imaginary part square. Real part is 1, imaginary part is omega by 4. So it becomes 1 square plus omega by 4 whole square. Similarly here, real part is 1, imaginary part is omega by 2. So square root of 1 square plus imaginary part square. This is how we take the magnitude. We have discussed these things already. Now we move into, we have to, in a Bode plot, we have to express the magnitude in decibel. So we will be expressing in 20 log of magnitude. So you know in what is advantage of logarithm? Multiplication becomes addition. So 3 by 8 into omega. So it becomes like plus. And the division terms comes as subtraction. The division terms comes as subtraction. Now we are written the magnitude in decibel. Okay. Right. Now we can see what is the phase angle, right? What is the phase angle of j omega? It is 90 degree. What is the phase angle of 3 by 8? 0 degree. So I didn't mention 0 degree. No need to record, no need to mention 0 degree, right? For j omega it is 90 degree. For denominator the angle becomes minus, right? For the numerator angle becomes plus. So what is the phase angle of 1 plus j omega by 4? Tan inverse of omega by 4 by 1. So times omega by 4. What is the phase angle of 1 plus j omega by 2? Tan inverse of omega by 2. Okay, thereby we got two things. One is the magnitude and another is the phase angle of the given transfer function. Okay. Now important thing is we have to decide what frequencies we are going to plot. Okay. So we know we have already from the question itself we have found out what are the corner frequency. First corner frequency is 2, second corner frequency is 4. We have to assume the frequency such that one frequency is less than the lowest corner frequency, another frequency is greater than the highest corner frequency. Okay. So we take first omega range from 0.1 to 0.1 to less than omega c, that is omega c1. Omega c1 is 2. So omega is between 0.1 and 2. Why I am taking 0.1? Because first corner frequency is 2. So I am assuming a frequency less than 0.1. It can be any value, 0.1, 0.01, 0.2, any value. But it should be less than 2. Okay. Right. Now you will find out, you know, look at this expression, magnitude expression, right? In Bode plot, magnitude plot is an approximate plot. Magnitude plot is an approximate. Phase plot is exact. because of this approximation only, we can draw the Bode plot very quickly. That is the advantage. This approximation is an advantage, right? Okay. Now we can look at the terms, right? This is the manifold response. Okay, it is having 4 terms. And we are taking a frequency omega between 0.1 and 2. We know very well that this term will function, will work after omega equal to 4. This is the scalar frequency. And this term will work after omega equal to 2, right? And this constant and this 20 log omega, those things we are seeing the first slide already, right? This constant omega, that is your S, 1 by S, these will be functioning at all frequencies. But 1 by S plus A will function only after A. S plus A will function only after omega C equal to A. Before that frequency, their contribution is 0. Okay, that is what we are seeing here. Now, I am taking a frequency between 0.1 and 2. 0.1 and 2. Right? Between 0.1 and 2, this term will function only after 2. This term will function only after 4. So, between 0.1 and 2, only these two terms will be functioning. 20 log 3 by 8 plus 20 log omega. Okay, right. Okay. Next we go into the next frequency. That is between 2 and 4. Next frequency. That is called first corner frequency and second corner frequency. 2 and 4. When the frequency is between 2 and 4. Right? Okay. Between 2 and 4, this term will function at all frequency because it is a constant. This is omega, that is the number S. It functions at all frequency. Between 2 and 4, that means I have crossed 2. Yes, because this term will work after omega equal to 2. Now I am between, omega is between 2 and 4. So this term will also function. Okay, but this term will function only after 4. Okay, so on basis of approximation, what I can do, this 20 log square root of 1 plus omega square by 4 can be written as omega by 2 whole square. For omega greater than 2, I can ignore the 1, so it becomes 20 log omega by 2. Bode approximation, right? We have seen in the Bode basics part 2 lecture already. Okay, so I am writing this term is functioning. This term is functioning. This term is functioning. This term is functioning. Okay, so that's what I have written, right? Right. Now for omega greater than 4. Omega greater than 4, all the terms will be functioning. This is constant, will function at all omega. 20 log omega will function at all omega. And after 4, this term will also function, right? Because the corner frequency is 4. After 4 will function. So based on Bode approximation, if I ignore the 1, it becomes square root of omega by 4 whole square. Square root and square gets cancelled. So it becomes 20 log omega by 4. Okay. And this term will also function, right? So it's like this term will function. Okay, all the 3 terms will be functioning, right? This term will function, this term will function, this term will function, this term will function. For omega equal to omega greater than 4. Right? So I'm just making like the blue tick mark. The blue tick mark, I can select it for it's a blue tick mark, right? And I can have like yellow tick mark. Yes, now it will be convenient for you. Wherever I have yellow tick mark, those are the terms functioning, right? Okay. Now we will find out that frequencies, right? At omega at point 1, omega at point 1, between point 1 and omega equal to 2, this is the expression. Between 2 omega between 2 and 4, this is the expression. Omega greater than 4, this is the expression. Now I will find out at each point, omega at point 1, I will substitute omega point 1 in this expression. I found out that it is minus 38.5 dB. For omega equal to 2, I substitute in this expression, I got minus 2.5 dB. Then greater than 2, okay, at 2 we have found already. Okay, this is at omega equal to 4, I have substituted, I got this value. Then omega greater than 4, I got this value, right? Okay, now we got the points. We got the magnitude for the corresponding magnitude for each omega. Okay, this is the plot that we are going to say. This is magnitude plot, right? Before going to magnitude plot, we have to see, we will be plotting things in a Bode plot in a semilog sheet, right? This is a semilog sheet. If you look at the semilog sheet, we can see this y-axis is evenly spaced. The distance is equal, right? That's why I say it's linear scale, equal spacing. But if you look at this, it's not equal. Look at the distance between this line and this line, it's more. It's reducing, it's reducing, it's reducing, it's very much less. Now it's very small. So it's non-linear. I can say it is logarithmic scale. X-axis is in logarithmic scale, y-axis is in linear scale. Okay. And the purpose of using why it is called semilog, it's very clear that out of this x-axis and y-axis, x-axis is in logarithmic scale. That's why we say it is a semilog sheet. Semilog sheet is mainly used for an electronics communication people to plot the frequency response, right? We will plot the x-axis in as frequency, y-axis is for magnitude and phase angle. That is called frequency response, right? This is how a semilog sheet will look like. Okay. One side it is in logarithmic scale, x-axis is in logarithmic scale, y-axis is in linear scale. We can see the distance is equal, right? Now we'll plot those values. We have already found that the values, right? I am taking, okay, before I missed out a point there, you can look here very closely. The lowest frequency I am taking is 0.1. I should not take 0. We'll understand it later why. If it is 0.1, since the logarithmic scale, next point is 10 times. 0.1 into 10, 1. Next major line is 1 into 10, 10. Then 100, 10 square, 10 cube, 10 power 4, 10 power 5. Okay. Now, if this is 0.1, this is 1. The next line is 0.2. This is 0.3, 0.4, 0.5. If this is 1, this is 2, 3, 4, 5. If this is 10, next is 20, 30, 40. If this is 10 square, this 100, 200, 300, 400. This is how we will plot the frequencies, right? Okay. Why I should not take 0? If I take 0, I cannot multiply by 10. So rest will be 0, 0, 0, 0. So I have to take the lowest frequency. It can be 0.1. If I take like, instead of 0.1, if I am taking 0.01, what happens? This becomes 0.1. This becomes 1. This becomes 10. This becomes 100. This becomes 1000. This becomes 10,000. Okay. Likewise, based on the frequency range, we have put the lowest value. We cannot put 0. We have to put the value very close to 0. Okay. Fine. Now we will plot those things. Already we have found out something like at omega equal to 0.1, I got the value of minus 38.5 dB. This point is minus 38. This point is minus 38.5. dB at 0.1. Similarly, at 2, it is minus 2.5. At 4, it is minus 2.5. At 40, it is minus 22.5. Okay, at 40 it is minus 20, minus 20 is here, so between minus 30 it is between somewhere here. Now we will make connect using a straight line. Okay, right. Now you have to think how I have arrived this from from these values I have plotted the magnitude plot. Okay, but before going straight away to the graph, we have to use our common sense and understand that is our answer is correct. Roughly we can draw the plot. Okay, let me help you how to draw the plot roughly. Okay, let us see that this is the transfer function we have, right? This transfer function is having how many factors? This is a constant, right? Constant. This is 0 at origin. This is pole at minus 4. This is pole at minus 2. Okay, among these four terms, what are the terms which are going to function at all frequencies? These two terms are going to function at all frequencies. Okay, we have seen in the first slide. Okay, then when this term will function? After omega equal to 4. When this term will function? After omega equal to 2. Right? So, before omega equal to 2, what are the terms going to work? Before omega equal to only these two terms, 3s is going to function. Okay, right? So 3s, now roughly we are not going for the exact thing, right? Roughly, right? 3s. What is the slope of s? 3 is a constant, right? It is constant, right? The magnitude is a constant. For s, the slope is plus 20 dB. Agreed? Okay. So when omega is between 0 and 2, only 3s is going to function. The slope is plus 20 dB per decade. Right? Next, I am exceeding 2. I am exceeding 2. Omega is greater than 2 but less than 4. What happens? What are the terms going to function? What are the terms? See, 3s is going to function at all terms, all frequencies. S by 2 is going to function after omega equal to 2. So 3s divided by s plus 2 is going to function. 3s by s plus 2 is going to function. 3s by s plus 2. Three s by s plus 2. Okay, and we know what is the slope of s? It is plus 20 dB. What is the slope of s plus 2? It is minus 20 dB per decade after common frequency. What is the result? Plus 20 minus 20. The result is 0 dB per decade. Okay, that's what we are seeing here. Between 0 and when the frequency is between 0.1 and 2, it is plus 20 dB slope. Between 2 and 4, the slope is 0. Okay, then for omega greater than 4, what are the terms going to function? This term will function, 3s is going to function at all frequency. S plus 2 is after 2, s plus 4 is after 4. So greater than 4 means all terms are going to function. So 3s divided by s plus 4 into into S plus 2. Okay, what is this contribution? This contribution is plus 20 dB per decade. What is this contribution? Plus 20 dB per decade. What is this contribution? Plus 20 dB per, sorry, these two are minus, extremely sorry, minus 20 dB. For this is also, it is minus 20 dB. For the denominator it is minus 20 dB per decade. Okay, what is the net result? You have to add plus 20 slope, minus 20 slope, another minus 20. So the net is minus 20 dB per decade. Minus 20 dB per decade. That is what we are seeing here. Right. Next we move to the phase plot. Phase plot, from the given transfer function, we can see if we can easily find out the phase, right? We have to vary the various values of omega. We have to find the phase angles. We have to plot the phase for corresponding point. For point 1 it is 85.7. For point 5 it is 69. For 1 it is 49. For 2 it is 18. For 5 it is minus 29. For 10 it is minus 57, right? Okay, so and you have to remember that phase plot is a exact plot. You never do any approximation. Okay, now we have got the phase plot and magnitude plot. Now we move into the graph, right? Is the thing we have plotted in the blank paper, right? We have plotted the magnitude in the white paper, right? Instead of that, we are going to plot the same thing in the graph. As we have said earlier, I am going to take the omega in the x-axis, magnitude, that is 20 log magnitude in decibel in the y-axis. The frequency range is 0.1 to 10. Okay, I am taking, and what are the corner frequencies? The corner frequencies are 2 and 4. This is your omega C1 and this is your omega C2. Okay, and at the omega C1, what is the value? It is minus 2.5. At omega C1 the value is minus 2.5. This is minus 2.5. This is minus 38.5. Okay, that's what. At point 1 the corresponding magnitude is minus 38.5 dB. At 2 the corresponding magnitude is minus 2.5 dB. At 4 it is minus 2.5 dB. At 40 this is 20, 30, this should be 40. At 40 the corresponding magnitude is minus 22.5. This is minus 22.5. This point is minus 22.5 dB. We got the, now we plot the magnitude plot in the graph itself. I can also plot the phase angle. For that, what I have to do here is I have to go for the degree here, right? Like in the same graph, I can make it like 0 degree, 30 degree, 60, 90, 120. Here it is minus 30, minus 60, minus 90, minus 120, like that. I can even plot the phase plot in the same graph. Okay. Now, very important thing. See, the purpose of the plot and to find something regarding the stability and to find the gain to meet certain condition. That's the main purpose of plot. But until now, we have seen how to plot a magnitude response and phase response. We go a step further to find out some two things like gain crossover frequency and phase crossover frequency, omega GC, omega PC. Gain crossover, phase crossover. Okay, gain crossover, what is the meaning? The frequency at which the gain becomes 1 or magnitude becomes 1. Okay, this I will say in polar plot, or else if I go for a Bode plot, I will take the magnitude in 20 log, right? So gain is 1 means 20 log 1 becomes 0 dB. So two definitions I can say for gain crossover frequency. It is the frequency at which the magnitude becomes 1 or the magnitude becomes 0 dB. dB scale means 0, normal magnitude is 1. We are studying polar plot, we will see these things, right? We never take 20 log in polar plot, we will take only the magnitude. Okay. Then something like phase crossover frequency, the frequency at which phase angle becomes plus or minus 180 degree. Okay, at some frequency the phase angle becomes plus or minus 180 degree. Here at some frequency the magnitude becomes 1 or 0 dB. That frequency is called gain crossover. If the phase angle becomes 180 degree or minus 180 degree, that frequency is called phase crossover frequency. Once you found out the gain crossover, phase crossover, we are ready to find out the gain margin and phase margin. Gain margin and phase margin means how much gain I can adjust. You know, the system can be like stable, marginally stable and unstable, right? We have three possibilities. So if a system is stable, how long it is stable? How much gain I can adjust until it becomes unstable or margin, and until it touches the margin of stability or instability. Okay, we will see those things, right? Gain margin. What is gain? Simple. Just it is 1 by the magnitude. 1 by the magnitude at what frequency? Omega Pc. So to find the gain margin, first we have to find out the phase crossover frequency. Okay. First gain margin, to find the gain margin, we have to find out the phase crossover frequency, and we have to substitute it in the magnitude and take 1 by the magnitude. We get the gain margin. This is how we work with the polar plot. But in Bode plot, what we will do is 20 log 1 by the magnitude at phase crossover frequency. So denominator 1 by becomes inverse. So minus 20 log magnitude, minus 20 log magnitude at what frequency? Phase crossover frequency. So just remember that to find out the gain margin, we have to find the phase crossover frequency and take that frequency, put it in the magnitude, okay, and take inverse. We get the gain margin. Or else in Bode plot, you just find out the magnitude at omega Pc and put minus sign before it. Okay. Gain margin is nothing but 20 log magnitude at phase crossover frequency. First to find out phase crossover frequency, then you take 20 log magnitude at phase crossover frequency, put a minus sign. That's it. Then phase margin. Phase margin. What is phase margin? Is nothing but 180 degree plus a phase angle at omega GC. So to find the phase margin, we have to find first the gain crossover frequency. After finding the gain crossover frequency, we can easily find out the phase margin. Okay, 180 degree plus phase at what frequency? Gain crossover frequency, right? Okay. Next, something like, if we can also say stability based on the gain margin and phase margin. If the gain margin and phase margin both positive, we can say the system is stable. If both are negative, we can say the system is unstable. If the gain margin and phase margin are 0, we can say the system is marginally stable. And there is one case is sure, we cannot have gain margin positive, phase margin negative. It is not possible. Both can be positive, both can be negative, or both can be 0. Only 3 cases can exist, right? Okay, that's it. Now I think we can roughly see how to plot quickly. You can see how we can plot some polar plot for a given function, right? G of s given as 2 by s, s plus 2, s plus 4. Okay, roughly, not exact plot. How many factors are there? We have a constant, we have 1 by s, we have 1 by s plus 2, we have 1 by s plus 4. We have 4 factors, right? And what are the factors will work at all frequencies? 2 by s at all omega. Okay. And what are the corner frequency? The corner frequency of s plus 2 is omega c1 is equal to 2. For this, omega c2 is equal to 4. Okay. So this term will function 1 by s plus 2 will function after omega greater than 2. Similarly, 1 by s plus 4 will function or will work after omega greater than 4. Now I am going to take a frequency like between 0.1 and 2. 0.1 and 2. How many factors are there? 1, 2, 1, 2, 3 and 4 factors are there. At all frequencies going to function. 1 by s plus 2 will after omega greater than 2 only. This is after 4. So what are the factors going to perform? Going to work? Only 2 by s is going to work. 2 by s means what is the slope? You know, for 1 by s the slope is minus 20 dB per decade. Okay, then what happens when between omega is greater than 2 and less than 4, less than or equal to 4. Greater than 2 means what are the term going to function? Greater than 2 means this term is going to function, this term is going to function, right? So it is 2s divided by into s plus 2. Okay, so this contribution is minus 20 dB. This contribution is another minus 20 dB. So what happens? The net contribution is, if I go for a plot, this is 0.1, this is 2. Between 0.1 and 2, the slope is minus 20 dB per decade. Between 2 and 4, the slope is minus 40 dB per decade. Because minus 20, it becomes minus 40 dB per decade. Then for omega greater than 4, what happens? All the terms going to function, that is 2 divided by s into s plus 2 into s plus 2 into s plus 4. Okay, so we know for each term is minus 20 dB, so together it is minus 60 dB per decade. So it is after 4, it is minus 60 dB per decade. This is the approximate Bode plot. Okay, if we look at another one more example before winding up. G of s is equal to 3 into s divided by s plus 1, s plus 4, s plus 2, s plus 6. Okay, how many factors are there? 1 constant, s 2, 3, 4, 5, 6 factors are there. That is, constant is there, 2 zeros are there, 3 poles are there, 6 factors are there. Okay, I'm going to quickly draw. That's our agenda, right? We have to draw it very quickly. That's why, because approximately we are drawing, right? We are not going for the exact value. Approximate shape of the plot we are maintaining, right? So this 3s at all omega, right? What are the corner frequency? Omega C1 equal to 1. Corner frequency of this is 1. Corner frequency of this is 4. Corner frequency of this is 6. Corner frequency of this is 2. We have to put in ascending order. So omega C1, omega C2, omega C3, omega C4. Right? At all omega, 3s is going to function. So what is the slope? It is plus 20 dB per decade. Okay. between 0 and 0.1 and 1. 0.1 and 1, it is plus 20 dB per decade. Okay, after 1, out of this term, when the s plus 2 will function after omega equal to 2, s plus 1 is after 1, s plus 4 is after 4, s plus 6 is omega after 6. So after s plus 1 this will function. Already 3s is plus 20 dB, this is minus 20 dB. So the resultant is plus 20 minus 20, it is 0. Okay, then 2 is coming. 2. After 2 numerator will this will function, right? This will function. So another 20 dB until 4. 4 means denominator this will start functioning. So again it is 0. Then after 6, this is so 0 dB, 20 dB, 0 dB, minus 20 dB. This is approximate Bode plot. Okay, phase plot is an exact plot that you can go do it very easily. Okay, that's it. Thank you.